the system. Yeah, go hide it. Go down this one, just hide it. Now you can start it.
Thank you. I just want to check if it's working. Anyways, let's start.
Waiting for something?
No, I'm ready.
Good stuff.
Okay, so today I'm going to be talking about the work which I started last semester when I visited Salil in Oak Ridge. And so essentially in this work, what we want to study is the effect of sulfate aerosols on atmosphere and upper ocean. And we do it with the help of a fully coupled model, CESM version 1.1.2. So here's the outline of the talk. So first few slides, I'll be giving an introduction, wherein I'll be talking about the basic definitions, different types of aerosols, their transport, and their, in brief, the effects. Next, I'll move on to the model details and the experiment details. And the rest will be the result slides, which will be what's the perturbation and the different kinds of responses. And in the end, I'll summarize. So the introduction. So first, what are aerosol particles? So any particles suspended in air, either liquid or solid, can be considered aerosol. So there are different ways of classifying them. These are the three main ways of classifying aerosols in the atmosphere. Primary aerosols are the ones which are directly emitted from the processes. The secondary are one which are not primary. They are not emitted directly from the sources, but they are converted from gas to particle conversion in the atmosphere. The other classification is, so either of these primary or secondary aerosol particles can be classified as a natural or anthropogenic, depending on the source, as the name suggests. And the third classification would be whether they're depending on the size of the aerosol particle. It could be called Aitken, accumulation, or coarse. And so what you see here is the distribution, the number distribution, the surface area distribution, or the volume distribution for the typical setting of an aerosol particle. And on the x-axis, you have the different diameters. So as you can see, so when you have a number, when you do a number distribution, these are the log normal distributions of aerosol particles. The first one is the number distribution, and what you see here is there are two modes which show up in this. So this particular mode, which is anywhere from 0.01 micrometer to like it's close to 0.1 micrometer, that would be nothing but an Aitken mode. And the mode which stands out in the surface area is the accumulation mode, and it's the next higher mode of a size available. And the third one is the coarse mode. So typically the coarse mode is mostly the sea salt and the dust, mineral dust. Accumulation mode, Aitken mode, can have both the primary aerosols as well as the secondary aerosols.
So what do you mean by health classification?
Okay, so for different fields,
good or bad for you, is that what it is? Health.
So if you want to study clouds or if you want to study health, you want to concentrate on the number distribution, because that's so the smaller particles shows up only in the number distribution. Whereas for the visibility, when you're talking about the visibility and hazy and non-hazy days, you want to be probably concentrating on surface area, which shows up this accumulation mode. And health, actually for health, you also, so this volume as well as number, both are important. Health, by health we mean mostly the respiration diseases through lungs.
So can you actually see through the clouds?
Sorry?
Can you actually see through the clouds?
These are
For
aerosols.
visibility.
These are not clouds, they're aerosols.
No, he's saying that.
No. What I mean is if you want to study cloud radiative
Well,
effect, I get it.
understand, but
No, you cannot.
It's a little funny.
You cannot. You cannot.
Yeah.
You cannot.
Tarun,
Mm-hmm.
there should be some correlation between the middle panel and the bottom panel, no?
Yeah, I also would ask the same thing.
Surface area and volume,
Well, I guess you're asking why you don't see coarse mode in any of the others. Is that right?
something like that. At least
So-
surface area and volume, there should be some, I think so.
So
Surface
no,
area.
so the way to think about this is, so when you're talking about the number, it's like, so in general the typical distribution of aerosol is such that there are a large number of smaller particles, right? So this is not just like a surface area and volume. It's also multiplied with number of particles available. So that's the main thing what you have to remember here. So that's why you don't see the same thing.
So these graphs are made from, do you know what data, like,
This is a typical
okay.
typical.
It might be a sketchy one.
No. This is, I think it's from a data, but this is a typical.
Typical.
If you look in any atmospheric chemistry book, they would show you this if you want to talk about the distribution. This is how typical distribution would look like. Okay. Yeah, but this is just mostly informative of these three modes and what diameter they belong and what field of study they are important.
So x-axis is the same for all of them, right?
Yes, it's same for all of them. You can actually put them in the same thing. It's just that what essentially this graph shows is if you want to talk about the surface area, if let's say if you sample today somewhere the aerosol particles and if you do the surface area distribution, you would mostly only one mode will stand up. Though other modes are there, but they're not seen. That's it. It's not that they're not there, they're there, but the surface area, this particular mode will dominate. Okay. So next, I want to show a movie. So this is produced by NASA. What they have done is they have these 5 different kinds of aerosol: dust, organic black carbon, sulfates, and sea salt. These almost act like a tracer, and they have given it a color coded. And it's essentially a movie based out of model GOES 5, and I think they have it on it's like multi-day levels. And I'll see if I can play this or not. Okay, if I can't play, I think that's going to be an issue. It's a
Click on that.
Or is it QuickTime?
It's a QuickTime.
Windows.
Yeah, that's why I wanted to get my laptop.
If it is available online, you can separate the browser. Right?
Yeah, you can also do it.
We can try that because it's
Right,
a
You
yeah.
can right-click and add HTML in.
But it's still a QuickTime file, right? Just Google for
they only have
QuickTime.
there is one on YouTube. I will try to show that. I think YouTube might
Yeah,
be.
just go to YouTube and YouTube will show up here.
They recently released this one, right?
No, this is very old actually. This is the old. I think the type goes 5. So let's see if you can find it. This is somebody has uploaded it. I think it's one of them. We can try one of these.
Maybe the next one.
Yeah.
Yeah.
So essentially, this is what you see here. So again, so the red is dust, green is black carbon, organic carbon, the white is sulfates, and blue stands for sea salt. So you can look at it, how atmospheric circulation moves around these particles, and like it's most of the transport is in zonal direction, but it's a fairly large.
The brown is.
It's dust.
Yeah, it's coming off Sahara, right?
It's dust.
This is a very nice picture. It shows not just aerosol, it shows the storm tracks, it shows the
Yeah.
history.
Yes.
Everything together.
Everything,
Right.
all
So
the
it's like
dynamics.
You can even see some of the sea salt being trapped in a cyclones and
Yeah.
things.
This kind of went viral, right? This video.
Yeah, I'm pretty sure it's a very informative video and
Right.
very nice visualization of
The sources also.
Amazon convection.
Amazon convection sea. You see, in fact,
Yeah.
like
Yeah. Why does dust goes from the east to the west? Other components goes from the west to the east.
so, this is mostly
Okay, yeah,
tropics.
you should know. You don't know the answer. Did you study any atmospheric dynamics? The winds in the tropics go that way.
So in tropics, mostly the winds are this way, and in the mid latitude winds, usually the typical structure is that way.
Easterly, you have tropical trade winds.
Trade
But
winds.
dust goes to such a high level.
Dust doesn't go that high. It's in lower troposphere.
So yes, and the mean flow is about 500 hectopascal, right? So I don't think the dust would go to such high.
So no, so essentially, I think what they've done is it's a column integrated thing. It's not just. It's like I'm pretty sure that some of them are at different levels. Some of them are at different levels, but so mostly I think this flow what you're seeing here is this is on a higher. This is on a higher elevation, whereas this flow what you're seeing it's on a lower
So
elevation.
you're saying that mid to upper levels, why you expect easterly flow? Is that what you're saying? Yeah, but this is integrated, column integrated. I think.
It's like essentially what I think the point of the movie is they just they want to show how well the dust moves from one continent to another. In fact, sometimes if you notice some of the dust which comes out of here, you can see it even. It's like comes here and then this moves. So it's a lot of dust. So yeah, but for this particular talk, I'll be mostly concentrating on the white part, the sulfates part. It's a nice informative video which I thought I'll show.
Yeah. The green thing,
Mm-hmm.
black carbon, why is there so much in North America and Central?
It's organic carbon and black carbon both. It's
Organic carbon corresponds with forest.
No, I think it's industry again. I think it's industry. So it's
So black carbon is really carbon, and organic carbon means hydrocarbons or stuff like
must be So there you have all these something called secondary organic aerosols. So
But the South America, north of South America part corresponds with forests very well, no? The green part that
this part is mostly Amazon.
yeah.
Yeah, but I think so. It's
Black carbon is soot that we burn
Yeah.
something.
Yeah, but that is
so-
kind of anthropogenic, I don't.
Yeah, black carbon is simply anthropogenic.
I'm just wondering
Burn
why
the
such
forest
a big
or burn-
area should be green. Anyway, and India looks very kind of confused, no?
It depends on what. It basically depends on what time of the year it is.
Yeah,
So unfortunately they don't have a. You would even see that. So this is for a whole year,
Yeah.
but it's on a very high resolution, temporal resolution. You would even see that during the summer season during May, June, July, you would even see the wind reversal and then it's become
Clearer.
no, it's very messy then.
It's messy.
It's very messy then. It's very
But
messy.
on an average, India looks green, I guess.
Yeah, that's mostly. But yeah, like, shall we go to the next one? Yes, but it's a very nice video. It gives you a lot of information.
I think the green part is also because of forest fires. I was wondering about that.
It could be. It
Forest
could be
fires.
carbon. So that's the only way they have put the carbon there. Okay. Right.
You can get rid of the bar at the bottom.
Right. Okay. So next, after showing you the typical aerosol transport, and so let's get a little bit of a physics. So what this graphic shows here is, this shows the aerosol and radiation interaction, as well as aerosol and cloud interaction. So typically, if you look in any literature, you would find direct effects and indirect effects. What are direct effects? So aerosols, these particles suspend in the air, they can directly interact with the solar incoming insolation. They can either absorb the radiation or scatter back. So essentially, this direct effects. So this is the way they divide different effects. So this direct effect is nothing. It's just about how much of the incoming solar radiation is being scattered or absorbed versus absorbed. And the rest all is aerosol cloud interaction. So let's get one by one. So essentially, this is an unperturbed cloud where you see cloud droplets bigger in size, and there is some rain. This is a nice cartoon, and what it essentially says is, so this is the incoming solar radiation, and a part of it is reflected back, which is shown by a thin line. So now so this is the first indirect effect. It's also called Toomey. It was discovered as early as in 1974, and what essentially it says here is, so when you have these aerosols present, so these small aerosols which are suspended in the air, they can act as they can provide a surface area for droplets to form, or for vapor to condense on. So essentially what happens is, when you have a lot of these cloud condensation, these are called cloud condensation nuclei. So when you have this lot of cloud condensation nuclei, what happens is, so the same amount of liquid water gets divided again among many small suspended particles. So the droplet size reduces, and it's typically when the droplet size reduces, it has a direct correlation with amount of light it reflects back. So to summarize this part, so when you have a more cloud condensation nuclei, your effective droplet size reduces in a cloud, and the reflectivity of a cloud will increase, which will reflect back more of a solar incoming radiation. And so this is called the first indirect effect. There are other indirect effects. So this one they talk about, these are the different second indirect effects. The first one it says here is, so now since your droplet size has reduced, so the precipitation will also reduce, because for precipitation to happen, my droplet size should go beyond a particular critical threshold. So the drizzle suppression and increased liquid water content, will again change the brightness of my cloud and can reflect back more radiation back to the space. The second one is, so now since the droplets become smaller, so they can be easily, by the updraft, so the air moving in the upward direction, they can be easily carried over to, easily carried up, and my cloud as a whole will shift up. So that's nothing but this increased cloud effect. So this can also do the same phenomena. It can increase that, and so essentially this wiggly line is the straight lines are the short wave, and wiggly line is my long wave radiation. So that's how we divide the radiation into two. And the third one is the increased cloud lifetime. So it's again, so all these three are interrelated. That's why they have put them in the same indirect effect, second indirect effect. So in this, what happens is, so now since your cloud droplets have reduced again, so my cloud will survive longer because of all these things, because there will not be much precipitation. It has also gone up. So all these three things are indirect effects. And so there is another effect. It's called semi-direct effect. Now let's say I have absorbing aerosols in the air. So the absorbing aerosols, what they'll do is they'll absorb the heat in the atmosphere. That will change the atmospheric temperature profile. So it's like part of my atmosphere is becoming warmer. So that in turn can affect my clouds, because my temperature profile is changing now. And in turn, so these are the three major classification of different aerosol.
So is this mostly black carbon, that absorbing aerosol? What are the absorbing aerosols?
Mostly it's black carbon. So and all those associated with the. So that's what. Yeah, it's mostly black carbon. So and other related carbons. So the scattering aerosols are mostly sulfate aerosols. Okay, so next I have another nice graphic which kind of illustrates this direct effect in little more depth. So let's consider the case A. So this is aerosol radiation interaction, also called direct effects. So essentially what they're showing here is, let's say if I have an scattering aerosols. Sulfates are example of this. So what essentially this is an incoming radiation, and these are so the other things what you see is the scatters. So what it says there is, it's going to block off my incoming radiation, and it's going to cool down under the layer where I have a lot of these scattering aerosols. And the B, what it what it tells here is, so my atmospheric circulation and mixing processes, what it would do is it would spread this cooling regionally as well as vertically. So this is one effect. The other one is, instead of that, if you have an absorbing aerosol, what could happen is, so absorbing aerosol. So if my absorbing aerosol is present in this layer, so it will heat up this atmospheric layer. And again, by the same principle, since a lot of the incoming radiation is getting absorbed in this layer, so this layer is not reaching that much solar wave radiation. So this will cool down. And again, what it says here is, so because at the larger scale there is net warming of a surface and atmosphere, because the atmospheric circulation and mixing process again distribute this thermal energy. So this is the basic introduction to the different ways aerosol can change my radiative balance of the atmosphere and can affect other things.
So if you assume the same amount of energy is coming down, then how will it be cooling and heating?
So
So basically what happens is, like, in a given layer, say aerosols.
right.
So it modifies.
So this is not in balance. This is right now not in balance. So it disturbs my energy balance of the system.
What's the question again?
So there is an intermediate layer which have aerosol,
Mhm.
and amount of radiation is coming in. So basically this affects the redistribution. Either it cools down that immediate layer or heats down the immediate layer. And the circulation will change the whole thing.
No, with the scattering aerosols, the surface is being cooled. The intermediate layer reflects the sunlight.
Right.
The scattering,
For the scattering, yeah.
What kind of
The absorbing is
aerosol
different.
scattering aerosol? What kind of aerosol is scattering aerosol?
sulfate.
Sulfates are
Industrial pollution. Like
industrial
smoke
pollution.
from factories, typically it's sulfate. Like it also leads to acid rain. Or volcanic eruption, that's sulfate.
So the bottom line is surface, right?
Yeah.
Yeah. This is surface. This is surface. Yeah. This is surface. This is surface.
It's like putting a mirror in the middle. Sulfate aerosol.
It just like whatever comes, it just reflects back.
Reflects back, okay.
It just reflects back. Or scattering, it could happen in any direction, but in general, like since a lot of it is coming this way, it will be scattered in different directions.
Yeah.
So this will receive.
That makes sense. If it is scattered back, then this can happen. Like,
Some of it is scattered back. That's
Yeah.
not all of it.
Not all of it. Not all.
There's a difference between scattering and reflection. Scattering in theory changes the frequency. No? It's absorption and re-emission in some sense.
I don't know if it changes the frequency, but it's
That
scattering happens
just-
in all directions. Reflection happens in whatever.
Yeah, direction is one thing, but the characteristics of the
That
radiation
depends,
changes
that-
with scattering, I think.
that
But
depends.
Reflection is the same thing.
Depends
both ways.
if it's elastic or inelastic.
Yeah, and I think we're getting.
No.
We have to,
Yeah.
more detail.
Yeah, I mean, if you want to go into detail, yeah, we can do all that stuff.
I
But
don't
this
know,
is
but if you're getting shortwave radiation that's scattered, it's still shortwave, isn't it? I don't think.
Well, yeah, but you can naturally change the frequency because of excitation. So
Okay, but how much?
will be in the same nearby wavelength, I guess. It won't be super different.
But as long as the shortwave doesn't become long wave,
it won't
doesn't matter.
become
Okay.
X-rays. Yes, but
You mean nothing very drastic.
Yeah.
very drastic. But yeah, this is the typical just, it's like, these are just very basic models.
I have a very quick question. Is there any process that has been implemented in those models to account for the breakdown of the aerosol particles, for instance, the black carbon? Or they're just passive traces?
No.
There are all kinds of.
They're all kinds of things.
So
various
in
degrees
theory,
of-
they can multiply, in a sense, they can break down.
So the one, so in the CAM5, which is CAM5, they have two schemes of dealing with the aerosols. It's called modular aerosol model 3 and modular aerosol model 7. So in one case, they have three categories. They have divided into three parts. Another, they have divided into 7 parts. So they have all kind of interaction happening between them. They have chemical reactions also happening. So right now, from the aerosol point, it's a step up from what we had before. So these get prognosed also.
So the person at ENCA who does this is actually the seminar speaker next week. He's doing
Yeah,
this
yeah.
aerosol, Hugh Morrison. I don't know if he's talking about this, but he's the aerosol model in CAM, I think it's developed by Morrison and CAM.
Right.
So it's a hot topic, this
Yeah.
parameterizers and aerosols. It's called prognostic aerosols, so you have aerosols, different
Yeah, yeah,
species,
sure.
and you track them and
Right. Yeah.
This is sinks.
Unfortunately, I'm not talking anything about that today. But I would have shown you just the basic picture. I should have shown you the basic picture.
So you mentioned sulfates, you mentioned black carbon. How about nitrates?
Nitrates also.
In which class they usually? I think probably cloud.
I'm not very sure. It's mostly, I think it would, nitrates are again, it would mostly act as a cloud condensation nucleus. So it would mostly come in an indirect effect. It's not, I'm not sure whether it scatters or absorbs, but I think it plays a role.
Oh, they do.
They do? Okay. But I think it will mostly play a role in the indirect effect.
Yeah, mostly people discuss sulfates and black carbon
That's interesting.
and marine sea salt.
Sea salt.
Those are the
Nitrates are a big
three
component
main-
of pollution.
Yeah.
You know.
They are
Hydrogen
definitely.
pollution, so.
But yeah,
Eventually see it,
nitrates
yeah.
are important in pollution. That's slightly different for aerosols.
Right, but I think there is a hazy line between.
Yeah.
Right.
Yeah, that's
Classify,
Yeah,
because sulfates are also from.
okay, NOx is a big contributor to pollution.
Yeah.
Right. Yeah, but I need to check up on, whether. But like most of the studies, they just, I don't know why, but they usually focus on sulfates or black carbon when they talk about climate.
Because they affect climate. The NOx
affect-
affects health, but not so much climate.
I don't know how much they can affect climate. I don't know.
Okay. Okay, so let's get to the specificity. So here's the model details. So I'm using CASM version 1.1.2. It's a fully coupled experiment where all the components are active. For the atmosphere and land model, the grid is finite volume close to 2 degree. That's the resolution. And for ocean and ice, which is it's mostly 1 degree, and it's displaced pole grid. And the forcings are from a pre-industrial time. And this is an experimental detail. So what you see here is, this is a control run. And each January marks are in these boxes. So what we do essentially in this case is we run one big control case for 40 years, wherein it's a pre-industrial forcing. So everything is so all the aerosol emissions are from 1855s, and I call this 1850S. S stands for sulfates. Next, what we did is we did a perturbation run, wherein the only thing different from the control case is only the emission files, only for the sulfates, are changed from 1850 to 2000. So I call that case 2000S. And so the perturbed case is run in such a way that every January acts as an initial condition for the perturbed run. So the perturbed run is not run for one continuous case long, but these are like only year runs. Why? The two reasons, like one is like we are mostly interested in an upper ocean. So if you can think of the climate state is mostly governed in this case by the ocean. And since we are interested only in the upper ocean, so I'm not running it longer than 1 year. That's another thing. And the second reason, I'll make it clear in the later part of the talk.
The emissions are from one case 1850s, one other case 2000. What about the meteorology?
Meteorology will change how the model develops.
So it is from 1950 to current, or?
No, meteorology means the other forcings.
Yeah, I mean, I'm wondering whether this experiment corresponds to a real period, or it's like an idealized kind of experiment.
It's a every year you force with the same thing. It's like a climatology, or not climatology.
Yeah, so it's not real from 1950 to 2000.
No, it's not real.
What about the initial distribution of aerosols? Forcings you change the forcings, right, for the perturbation case.
Only the sulfates emissions are changed, not the forcings, but only the sulfate emission.
So what about the sulfate concentration? It's prognostic aerosols are prescribed. These ones.
So
these are prescribed, I thought. These are prognostic.
The emissions are not. Emissions are prescribed.
Okay.
After it's being emitted, all that happen is prognosed. After the emissions.
How long does it take? What's the lifetime?
So typically they say it's only of the order of it's only of the order of weeks.
A couple of weeks.
Yeah,
so
and it's only another thing to say is it's very different from the stratospheric. It's only the emissions only in the troposphere what we are changing. It's not related to the volcanic eruptions and the emissions they would change. and it's just same. It's like whatever. So it's just given the same forcing every year. Same forcing every year.
Yeah. So for the meteorology, the starting the point is also the same.
Yeah,
Condition on Jan 1st on.
Exactly same. Exactly same.
Yeah, and the thing is just advocated around passive, or the tracer also, the sulfates also interact with the meteorology.
They do.
Okay.
They don't interact with meteorology, but they interact among the chemical species around, and the sulfates, if let's say if they interact with something, they can get so the sulfates aerosol, they can get rained out, they can convert it to another species, but they interact with meteorology in a way that they move around with winds, and
Right.
they interact with clouds.
Basic thing, yeah.
They interact with clouds, and all those things happen. Everything happens. Only thing is, the emission files are different only for the sulfates. Both sulfates as an aerosol as well as precursor gases. So sulfates are mostly primarily emitted at sea salt, as a sea salt. No, not as sea salt. So sulfates are mostly industrial emissions, plus they are secondary, plus they will be converted from sulfur dioxide or DMS, dimethyl sulfide. Okay, I think I'm giving too much information. Okay, so this is what the perturbation looks like, So between the two runs. So from now on, what all spatial plots I show, there will be always the mean of 2000 sulfate run minus mean of 1850 sulfate run. So this is how the perturbation looks like. This is a plot of annual burden of sulfates, 2000s minus 1850s. So now annual burden essentially, it's a term for a column integrated sulfate amount. So it's given in milligrams per meter square. Given in milligrams per meter square. So essentially what you see here is, so most of my aerosol loading, most of the aerosol change is in this mid-latitude belt. It's in this mid-latitude belt. And some of the regions, these correspond to the source regions. If you look in the emission files, you would see there is a plume of sulfates coming in this direction, there, and so forth in different places. And so that's how it looks like. And so these three boxes, I want to show how they change from January to December. So as you can see, the most of the peak in most of the places, Central Asia, Northeast China, India, Southeast US, Northern Hemisphere, is this whole belt, what I'm just denoting it as NH. And you can see they peak mostly in the summer times. Okay, so that's how the aerosol burden looks like. Now there is another parameter called aerosol single scattering albedo. It's a measure of the effectiveness of scattering relative to extinction for the light encountering the atmospheric aerosol particles. So what it means here is, so as I told earlier, right? So aerosols can be scattering as well as absorbing. So at any given point, they can be both scattering as well as absorbing happening. So essentially this, what it tells here is the scattering, it's a fraction of extinction, means both scattering plus absorption. Scattering is just a fraction of how much amount is getting scattered. So what this plot tells you here in this case is, so like though most of my burden was in this place, this place, but the scattering because of aerosols is happening as close to 60 to 80 degrees latitude also. So they are being, so though they don't show up in that, but it can be happening at different places. Another thing to note here is, so this is essentially an indication of the direct effects. Like I'm not considering any aerosol cloud interaction, but this is a kind of a proxy for where all the scattering is happening on the globe after I have released my aerosols. Okay, so the vertical distribution of the same. This is a zonal mean, that's the meridional mean. And Aitken is the smallest particle. Accumulations are a bigger range of particle, and cores are very big. It's only dust and sea salt. So one clear evidence from here you can see is the smaller particles with the lower mass can get advected vertically up in the atmosphere, and then they can both meridionally move as well as zonally move north and south from there. And so rest is detail.
This is the perturbation, right? Not the aerosol itself, the perturbation.
So so the way you have to imagine here is
there's not much in
1850. There are not many sulfates.
So 1850 is 0.
Not much, yeah.
So the perturbation is almost equal to the state.
For sulfates, yeah.
Yeah.
For marine salt, it won't be. But for
Yeah.
sulfates.
For the anthropogenic sulfates. For the anthropogenic sulfates.
So the picture we saw, the Ghost YouTube movie we saw,
Mm-hmm.
what do you see there? Is it mostly dominated by the lower tropospheric stuff? Because that would explain the question about why is it moving westward? Because if it's lower tropospheric, then the easterlies, the trade would dominate. But upper tropospheric, the winds are different.
But looking at this, yes, I think.
The lower,
Yeah.
so the accumulation of the
Yeah.
codes, not the
Yeah.
it's showing up.
I think so.
I think that answers your question, why it's moving.
Right. So yeah, then another interesting thing is, like, you can see that it's mostly concentrated in that belt, as you can see, like the mid-latitude belt, and I think this is somewhere in I think this is somewhere in Gulf, not in Gulf. Wait.
Go to Africa or Europe.
Yeah, Europe and Gulf region. That's, I think, China. I think that's India. So it's like different. Also, another thing is there is a variety. Different modes show up in different places. So it's an interesting thing to look at. Okay, so that's all about the perturbation, the kind of a perturbation we are introducing to the system. Now let's look at the responses. So the first one is the cloud response. So again, it's a difference picture: 2000 sulfates minus 1850 S. So there are some interesting features you can see, and so the yellow line indicates the significant difference area. So as you can see, there's a lot of cloud. The cloud has increased over the Southeast Asia, which are mostly associated. This is where most of the sulfates are emitted, and you can see that there is a lot of low-level cloud increase, not low-level, just a cloud increase even in this region, and there is a cloud increase over this region. There's a cloud increase over this region, and so this kind of shows how the clouds are being changed. The total cloud fractions are being changed. Now, if you want to think back how the distribution of my sulfates looked like, they mostly looked like this, but my cloud response is very different. It's like much more complex. So that is one thing to keep in mind here, is because this cloud response is not just because of the direct effects of sulfates. There's also indirect effects happening here. There's also atmospheric circulation or atmospheric variability which changes the response, and also I'm pretty sure even ocean variability at some point would be affecting it. That's why this cloud fraction looks very different from how originally my sulfates burden is over the region.
So do you know how much of the indirect effect is parameterized in this model? Because if you don't parameterize it, won't be there in the model. It will be there in the real world, but not in the model.
So I've looked up a paper, and so they have done a comparison study from ARM data, and I think this is limited to particular sites. And what they say, according to what they say here, is the model is doing very good when it corresponds to first indirect effect.
So it is parameterized.
The first indirect effect only like.
Not that it's doing very good, but you have to put it in.
Yeah, it is there. It is there. It's doing it, and at those sites it's doing a good job according to the paper.
But what about the other indirect effects? Are they?
No. So I think it's only this what they talk about. I think and I think this is the biggest out of.
You might want to check, depend on the settings that turn it on and off. It's not by default.
Right.
So check what.
I need to check. I need to check. But according to
them,
the
other switches like turn on the indirect effect, turn it off. The reason they don't put it by default is people don't know how big the effect is.
Okay.
It's a huge unknown in climate change.
Right.
Because the sulfate effect can counteract global warming by 50%. So we don't know how big the effect is.
Okay. I need to look that up.
Yeah, check
the
run nameless files. I'll tell you what is turned on, what's not turned on.
Okay, I'll look that up. Okay, so that's the story, and probably this is the reason why, since my cloud response is very complex, it cannot be easily predicted from just the sulfates in the atmosphere, and probably that's why we have a big uncertainty when it comes to the radiative forcings due to aerosols, and even due to sulfates in that. And this is again the vertical structure. So as you can see, mostly this part is somewhere here. So it's essentially what it says here is, so this what you see, this response, the big response, is because of the change in the high clouds. and it's mostly, whereas this part is mostly due to the low clouds. Means if you look at it, you can decipher that, and that's the vertical structure. So after moving to the cloud response, let's move on to the surface temperature response. So which is we can relate more to, and so again the blue color here indicates. So after I added a lot of sulfates into the atmosphere, my surface temperature has reduced. My equilibrium surface temperature has reduced, and the red means the opposite. So as you can see, most of that mid-latitude belt, you see a lot of cooling around in that region. Now this could be, over this region we saw that there is also a lot of cloud change, and so most of this is happening because of the aerosol cloud interaction rather than because of the direct effects. Whereas in this region it could be both the direct as well as the clouds playing an important role. Whereas I think over this region it's mostly the way clouds have been changed, because you don't see much sulfates over this region. You don't even see much single scattering albedo plots which I showed over this region. So it's mostly that. So other than this significant belt, I want to point out two other regions. One is this tropical Pacific. There's a warming happening over this region, though it's not statistically significant, but still it's happening, and it's interesting. Why would this be happening? Another region, similar region, would be over this North American region. Why would there be a warming in that region? So essentially, why there is warming in tropical Pacific. In the later part of the talk, I'll be just giving a reasons to why to look at this region and why should we look at. So
has anybody studied, is the warming in North America robust? Does it happen in other models other than CSM?
I have no idea.
Good to check on that. I mean, just make sure this is not a statistical one.
Okay.
It seems unusual.
It seemed unusual, and why it's unusual is because most of my cloud radiate effect as well as the direct effects, they can explain only the cooling under the thing, as I shown in the cartoon figure. Scattering aerosols, direct can explain only. Yeah, that's important. So just to complete the picture, the precipitation is even more noisy, and we never get a very good signal. But there is a significant decrease in rainfall over this region. Now this could be again the indirect effects, since I have a lot of sulfate aerosols that can act as a cloud condensation nuclei. So my cloud droplet size will reduce, and because of that, my precipitation is reduced.
What about just the cooling?
It could be just
evaporation.
It could be just the cooling, but why I'm saying is because there is also increase in cloud, big cloud, lot of cloud.
But one way to check that, you run the model and turn off the indirect effect.
I need to look up, whether you can do that or not. I'm not sure.
Always turn off indirect effect model.
Okay.
Because as I said, it's an unknown parameter and it's a knob. There's no default setting because people don't know what the default setting is. And often you set it to 0 because you don't know what the number should be.
Okay. So I need to check that. Look
the
that
real
up.
world has the indirect effect, but the way to do it in models, nobody knows how to do it right.
Okay. So this is one thing we could check out. If you can play with the indirect.
It's possible the runs don't even have it. So if you start expanding it by the indirect.
But the thing is, most of the studies which they talk about, they never talk about switching off indirect effects or adding indirect effects. They don't talk about it. No, in the model itself, the modeling studies, they never talk about it.
Don't trust the model papers because nobody will be able to specify.
It is not a solved problem. The indirect effect.
It is not a solved problem. Even in observations, we cannot give the exact number.
What I'm trying to say is, modeling purpose will tell you only very minimal information. So it's very difficult to find this kind of detail from the publication. So
but before you give this talk in public, you need to know what the settings are.
Okay.
You can't what indirect effect is put there.
I need to look that up. I need to probably check that up, how aerosol and radiation interacts in CAM.
Yes.
Okay.
Not just CAM, the particular version of CAM.
Particular
There's no
version.
default.
Okay, I'll look that up.
The CAM4, for example, didn't even have a prognostic aerosol.
They had only bulk model, bulk
diagnostic aerosols.
Right.
The aerosol was just specified.
They're just specified, yeah. Okay, I need to look that up. Okay.
Tarun, yes, this is a change in precedence, right? In some sense, it's a perturbation.
Right.
Did you look up the pattern itself, how well the models are reproducing that compared to observations or? Usually the precision field.
There are obvious errors there are a lot of biases in model precipitation.
Usually they're decent, but not great.
It's one of the fields that's very hard to get right.
It is hard to get. Yeah.
In fact, actually, the proposal, originally it was to improve the precipitation over this region. It was the proposal was put in that way, because there were biases in that region. Okay, so after this, let's move on to the SST. So this is the SST response. As you can see, again, there is a big tropical Pacific warming over this region, and this is again you could see the earlier cooling pattern even in the surface temperature. Now let's concentrate on the tropical Pacific. Okay, before that, also I wanted to show the net heat flux at the surface. Again, the difference in the net heat flux. So it has short wave, long wave, latent, and sensible heat flux. Difference between the two. So as you can see, a lot of this cooling, this blue color corresponds to the blue color in this region, and but over this particular region where there is a big warming here, we cannot directly link it to whether it's the heat which is reduced, or it's the heat which is reduced or increased coming from the atmosphere into the ocean or not. We're not very sure about it. There are other features, like for example there's a lot more this region, whereas in SST doesn't show up that much. So now over the tropical Pacific, if I take a box over this region and I do a time series of those two runs. So again, my brown color indicates here it's a time series over this region, averaged over NINO 3.4 region, and the brown color is for the 1850 sulfate case, and the red case is for the 2000 sulfate case. And these dots are the initial conditions when they were started. So you can see there are a lot of times when the Perturb run is following very close to my control case, but there are a lot of cases where my Perturb case, suddenly there is an increase in the temperature over that region, this particular region, and also there is a decrease. Also, some places there are a decrease over this region. So this is another reason why we wanted to do a yearly run. It's because if you would have done one big continuous run as a Perturb case, so my ENSO state would have been very different from what it would be in my control case. If my Perturb case started here and it kept running, so my ocean state can go quite differently, and it can change my mean. So this is another reason why we wanted to do only yearly runs, so that I'm not allowing my ocean state to go very far over this region from the control case. So this is what you see here is a monthly data. So if you want to look at the annual response, what I've done here is, another thing to note here is, so it can also, so my initial conditions could be in different phase of my ENSO. So this is essentially my ENSO index. So the positive anomaly means El Nino, and negative anomaly means La Nina. So you can see my initial points are also differing. It's whether my initial condition was when the ocean state was in El Nino state or it was in La Nina state. So what I've done here is I have scattered. This is the average response. This is the difference between those two curves on this axis, average over 1 year. And this is the initial, what was my SST anomaly at the start. So most of these, the dots which you see in this, they are when my starting condition was already in a El Nino state or versus the La Nina state. So one clear distinction, one very clear, so first thing is you don't see any clear difference between La Nina versus El Nino. So it's my response over that region is scattered everywhere. But one clear thing what you can see here is most of my response is above the zero line. So what it says is most of the times there's a warming happening in tropical Pacific. So a warming is a preferred way in these runs. Why is it? That's what we are interested in. So this is annual average, but on a monthly basis you can. So this is again a difference between those two curves which you saw in the previous, red minus brown. This is how it evolves from January to December. the red line is the ensemble mean, rest all are the ensemble different years in those things. So as you can see that my response over that region picks up somewhere, you know, when somewhere at the start of the July, or you know, the summer season, when we expected the aerosols to also peak around the same time. Okay, so after talking all that, so in this talk I'm just talking about, you know, that there is this warming over tropical Pacific existing. Why is it existing? That's what we need to explore. So what I have plotted here is the subsurface over the Pacific temperature, the subsurface temperature over Pacific. This is the same sea surface temperature what you have seen in the earlier things. This is 5 meter, 55 meters, 105 meters, 135 and 155. So as you can see, over the tropical Pacific, my response is becoming stronger as I'm going deeper and deeper. And if you go further down around 200, after 200 meters, close to 200 meters, you don't see any response. So it's only in the upper ocean where the response is shown. So I don't understand this pattern very well. Why it's happening? What's happening with the tropical Pacific one? But another thing you can see here is, so this is because of the direct shortwave forcing over this region. As you can see, as you go down in the surface, the direct effect of aerosols is gone out of the case. Okay, so what I do next is that's the last plot, and what I'm showing here is I'm showing a cross section at 5 north, at equator, and 5 south. Again, it's a different picture. Okay, another thing I want to point out is, so this plot and the next plot, it's not from 40 years, it's only from 21 years. Like, we have lost some of the initial ocean data. That's why we are showing only for the last 20.
You're doing new run, right? It's not done. Are you extending it?
So this is like after extension. I haven't done that. You said
we need to extend it again once we settle on.
Okay. So the cross section looks like this. This is the 5 north cross section, equator, and 5 south. So again, you see there is a greater warming subsurface than at the sea surface, and these lines corresponds to 20-degree isotherm for each of these runs. So just a slight shift of that. So if 20-degree isotherm, if I can take it as a proxy for thermocline, then a slight shift in that indicates that the thermocline in one case is slightly lower or higher than the other case. So this is it. There is a warming here. Now, why is it happening? This is what we need to find out. And with that, I'll summarize today's talk. So we know that sulfates were confined to 20 north to 60 north belt with summertime maxima except over Indian subcontinent. There was strong scattering further north of 60 degrees despite lower surface burden in that region, as you saw. The vertical structure of the sulfates showed that there were upper level transports. The cloud response was complex due to aerosol cloud interaction, atmospheric and oceanic circulation variability. The surface temperature response over a large region had a signature of increased shortwave scattering, and the precipitation change, there was only significant precipitation change directly over Southeast Asia, and there is an indication of preferred warming response over tropical Pacific, though not statistically significant, which is difficult to explain with the known aerosol effects. And we see some interesting thing happening in subsurface temperature also. Why is it happening? Not sure. I appreciate any ideas and comments, questions. Done.
Winds.
Okay.
How you check the wind pattern between those stress?
Wind stress.
Can we go to Chrome?
Okay.
Why is this feedback?
It's here now.
Maybe laptop is on, or
My laptop is on. Do I need to?
Go to the settings and check the speaker output thing.
Tarun?
Yeah.
I have a question.
Mm-hmm.
Well, your control simulation is spun up, or
It is spun up. It's like we have taken an initial condition from one of the NCAR websites, and I think it's spun up for almost like 700 to 750 years.
Okay, well, looks curious because there's a strong response in the North Atlantic, especially in the deep convection region in the Lap Sea. If you look at this, what is it, the surface heat flux difference map you showed earlier.
Mm-hmm.
Yeah. Everywhere is, I mean, losing heat from the ocean,
Mm-hmm.
except in the Lap Sea.
Yes, yeah. I do not know why that is, but yeah, I also noticed that.
That may just be internal variability, but it's very long time scale. So you have two realizations, 1850 and 2000. They may just have different sea ice distributions. Possibly.
Okay.
And that part of the world is very noisy when it comes to modeling.
Okay.
Labrador Sea ice.
So it could be just some feedbacks. Okay.
Right, but this is the mean of the 40 mean, right?
40 years, yeah.
It's 40 years.
Oh, okay. Is the mean of the 40 difference, or just continuous mean?
According to the distribution, he only changed the emissivity, right? So the ice should be the same. I mean, to start with.
For the control case, it's 40 continuous years, and for the perturbed case, it's 40
1 year long.
40 1-year runs.
Right. So I'm asking whether it's just the continuous mean of difference or the difference of the mean.
It's
Should be the
The
same.
difference of the mean most probably.
It should be the same, it's linear.
Yeah, I mean.
yes, but I think you have a point.
Oh, you're right that it's natural variability doesn't play a role because we're not doing two different 40-year means. It's one 40-year mean, other is 1-year means, which are not very different from the 40-year because you're starting each year.
So can we, over this region,
So then there's something else going on there.
So can we say that, like in my control case, there is a longer term time scale variability over this region?
Yeah, no, what I said was wrong because I assumed that I thought there were two different 40-year means, but they're not. They're not. They're much closer because you're starting each year separately.
So why do you think this?
I don't know. I don't know the answer.
Yeah, I don't know either.
And any other questions? Ping, do you have any? Go to Chrome. Let's see. I think other ping was on. Ping, you seem to be muted. If you're talking, we can't hear you.
Yeah. Okay, I just turned it on. Can you hear me?
Yes.
Okay. Well, I mean, you actually see. I agree that the ocean response is definitely due to the change in the wind. It has to be because it's in subsurface.
So
I noticed that. I mean, if you think about it, right, the way you're doing that, it looks like you induce basically a cooling in the northern hemisphere.
So we just go there. Far away from
better.
But predominantly, you basically introduce the cooling.
feedback. Just go there.
So, Dr. Ping, what was the question?
I'm commenting on your response in the tropical Pacific.
Okay.
I think the fact that you actually see the subsurface response
Right.
definitely suggests there's a change in the surface wind.
Right. So
if you look at your response pattern, what I see is that after you change the aerosol, mostly what you're getting is a cooling in the northern hemisphere. Is that right?
Right.
So if you're cooling the northern hemisphere, which means that the atmospheric heat transport has to be compensating for that.
It has to be.
So I suspect that, I mean, if you look at your precipitation response, it looks like there's a shift of the ITCZ. So I think your tropical atmosphere is responding to the cooling. And therefore, I think there's a change in the surface winds.
Okay.
And the surface winds is actually producing a change in ocean circulation, equatorial ocean circulation.
So you're saying I should look at the winds?
Right. I think you can, if you're plotting, I suspect that, and for the same reason, I suspect that you probably see a change in the, it might be interesting just, plotting the heat transport in atmosphere. I suspect that you're going to see a change in the heat transport.
Okay.
And then the heat transport have to produce a Hadley circulation change, because you can't stop near the equator. It has to be changed across the equator.
So another
and some of this thing could be also related to these issues. If you looked at Atlantic Ocean, looked at overturning circulation, you may actually see a change in the overturning circulation too.
Oh, is it? So only thing is you have only the Perturbed run is run 1 year.
That's all right. The equatorial Pacific would adjust very quickly.
Okay.
The atmosphere adjustment should be very quick.
Okay. Yeah. So I wasn't sure of that.
Then I think once you change the wind, once you change the tropical circulation atmosphere, in a couple of the system, these upper ocean would respond very quickly.
Okay. I'll look. I'll have to do a lot more analysis.
Yeah. Okay. So it might be interesting to look at the. I think it definitely should plot the difference in the wind stress and then the wind stress curl as well.
So I'm plotting that. I'm not showing.
It's responding to the change in the deep convection, and the deep convection change is probably related to the fact that you're actually cooling the northern hemisphere, so the atmosphere is readjusting its heat transport and compensating for the heat loss in the northern hemisphere.
Okay.
Hey, Pink, could you
Say that again.
Your volume a little bit.
Oh, my volume?
Yeah.
Okay. Is it better now?
Yeah, I think that's.
Okay.
So we are hearing.
Yeah, I don't know why. Maybe I was too far away from my computer. Maybe. Yeah. Anyway, those are very interesting. But isn't this a similar thing? Saramana, the postdoc we had.
Yeah. What she was long 40-year run.
Yeah.
So that changed. So we changed the experiment.
Right. But it's actually a very similar design, right? Except this is a 1 year, kind of a 1 year simulation. I remember, but the end results seem to be similar, right? I mean, you also, in her case, you also see a change in the tropical Pacific, I remember.
Yes. There was similar results, but we thought we could get it better.
Right. Right. It might be interesting, the fact that as a who pointed it out, the deep convection region, the LAP-C region changes, might be interesting to find. People have been speculating, the aerosols actually does have an effect in this thing, and that's actually, I was questioning. NCAR has been doing this decadal forecast. And one of the things they find is that actually the decadal forecast, they actually have quite a bit of skill in predicting the temperature changes in the North Atlantic Ocean. One of the questions is that how much of that was actually due to the external forcing they impose in their forecast.
Okay.
So it is possible that the aerosol may have an impact on this.
I have a couple of comments. So, which is responsible. So you get a depth function jumping for 1 year or so. See maybe difficult for observation.
Okay. Anybody else?
Can you reinitialize during the January year?
No, that one down. Okay. January.
So window also will be
It's exactly the same point I left. In the control run, the initial run, right restart run, everything there.
but the emission for the
And so,
and how can that from January to monthly basis?
why would that?
There's a seasonal lag, like the quarter, the season cycle. So you can make
You may want to, let's do at least this time of the year. Reality. It's starting always in January.
So you can see.
Okay.
You can also see.
Response very fast. It doesn't matter.
No, the time scale, but beat state is different.
That's what I'm saying. We use the time window. If you do say
Yeah, only for the same for the.
Then you can hold it, change.
I'll anyway comment. Okay. Anybody else? Any other questions? Good. Thanks.
Who's the speaker? Anybody know?
Who is going to be speaking, I think?
Yes, it's me.
Okay.
Thank you.
Thank you, everybody.
Okay.
Alright.
I'm going to be gone.
Okay, Sarvana, actually, I just sent you an email.
Dr. Sarvana.
Ping, I saw your email, so I'll get back to you. What thing?
Yeah, we need to think about this because I'm not sure.
Fees for the LOI. So I'll get back to you.
Yeah, you take a look and then get back with me.
Yep, I'll do that.
Yeah.
Subjects are also there in
Is Xiaohui around? Can I talk to Xiaohui a little bit?
Who?
Xiaohui.
Oh, Xiaohui? It's called Xiaohui.
And sea salt is anywhere. Sea salt.
Everything is there. I think the color.
No, but I think that's a very good You could see a lot of traveling things.
Hey, can you hear that?
Yeah, well, I can just call her, I guess. If she's around, right?
Yeah, she's here.
Okay, maybe I just call you, Xiaohui. Okay. I'll talk to you later. All right. Bye. Have a nice weekend, everyone. Bye-bye.